If this is x-axis and if this is y-axis, then x square by a square plus y square by b square equal to 1, where this distance is a and that distance is b, is called the equation of ellipse. And ellipse looks somewhat like this. It has got two foci, and the way ellipse is defined, foci play part in that definition. Circle is a special case of ellipse. When B and A become equal, then ellipse becomes circle. This is called the major axis. This is called the minor axis. So length of major axis will be 2A and length of minor axis will be 2B. So semi-major would mean A and semi-minor would mean B. Ellipse is there in coordinate geometry. So mathematically we will be doing extensively the discussion. Right now we are doing it from Kepler's laws perspective only. Kepler's laws are for planetary motion. The first law says that the planet moves in elliptical orbit and Sun can be in one of the two foci, this or that. So that's law number 1. So if we say that the planet moves in a circular orbit, then it only means that it is elliptical and ellipse has a particular case. So circle is a special case of ellipse. The first law about ellipse. Second law says that, now suppose I fix Sun here. Out of the two foci, I choose the left one. So planet is moving around the Sun like that. Second law says that if these two are the locations of the planet, and these two are also the locations of the planet, and if these areas are same, which areas? Or let me put it this way. And if these times are same, time to go from here to here and time to go from here to here. If these two times are same, then these areas will also be the same. Which areas? One I am shading here and one I am shading here. Any 2 points you take in the journey, same time interval, that you are getting by same time interval, and construct such area joining these 2 points to focus, These 2 points can be anywhere. Join them to the focus and shade this type of area. You will find everywhere same areas if times are same. Now it's pretty obvious that if in the same time I have to get the same area, then I will have to cover a longer path. If I don't cover a longer path, if I take a small path just like this, there is no way I can get the same area. Suppose I try to take exactly the same length here, what will happen in that case? I will get 2 points corresponding to these. If I join this, if I join that, where am I going to get the same area as this? And now that means that if you want areas to be the same, this distance has to be more. So this law, also called law of aerial velocity, constancy of aerial velocity. This law, which is about constancy of aerial velocity, is like saying that if the planet comes close, it tries to run away quickly. If the planet is far away, it goes somewhat slowly. If it comes close, it really runs, or the sun will swallow it type of thing, so I should run away. So the closer the planet is, the quicker it moves. Aerial velocity is always same. That is second law. So you can also write it mathematically as dA, A for area, dA by dt equal to constant. So this is a new type of velocity. We have been talking about velocity as dx by dt, but this is not dx by dt, this is dA by dt, area, change in area upon change in time. So that's law number 2, law of constancy of aerial velocity. Third law says that the semi-major axis t square is proportional to the semi-major axis cube. T square is proportional to the semi-major axis cube. That's law number 3. T is the time it takes to complete one full revolution. In case of circle, where A and B are same, and we call them radius. We call them radii, A equal to B equal to radius. So it becomes t square is proportional to radius cube. Let's now talk about the special case of circle. And this discussion is not just limited to sun and the planet. Any circular system you take, it would be applicable for that. So that's a special case that we are discussing. So why would a planet move around the sun in circular orbit? We know that for circular motion, and also we will take constant speed.